Okay, let's start our second lecture. Go to Google Collaboratory. Python can be used like a calculator. To run the code, you can press the play button or hold down Shift and press Enter. So press the play button or hold down Shift and press Enter. You can not only do addition, multiplication, and division, but also use variable. You might remember you remember something like this form. Your middle school or high school math. X and Y are numbers shown as letters. You can think of them as boxes that are prepared before actual number go inside them. These are called variable. In Python, you can also prepare named boxes as variable and put numbers or text inside them. For example, when we write x equals 5, it means we are putting them number 5 into x. In this case, we are putting 3 into y. So when we run this, x plus y means 5 plus 3. So 8 is printed. So for x times y, x is 5 and y is 3. So 5 times 3 equals 15 is printed. One important thing to note is that in math, x is just x, but here x equals means putting 5 into x. So the meaning is slightly different from math. For example, if we add x equal 2 here, in math, it would be impossible to have x equals 5 and x equals 2 at the same time. But in programming, we read the code from top to bottom. We put 5 into x, and then we put in 2 into x. So the program run in order from top bottom. When the program reaches this line, what happens is first x contains 5, then 1 contains 3, and then x now contains 2. So x plus y becomes 2 plus 3, which is 5. For x times y, x is 2, y is 3, so 2 times 3 equals 6 is printed. You can check a situation like that. This is Python tutor. We can check how to move computer. So first, we put 5 into x. Next, we put 3 into y. Next, and x now contains 2. So here, we will to from 5 to 2. So print 2 plus 3 is 5. 2 times 3 is 6. 2 minus 3 is minus 1. like that. Okay, so you can also put strings into variables. The plus sign here means connecting strings together. So hello and Alice. And so hello plus space plus Alice becomes hello Alice. Hmm. So you might have noticed a hash mark appear appearing in the code. This is actually for comments. The part after this hash mark do nothing. If you run this, nothing will happen. Nothing. Sometimes you want to comment to many lines at once. In this case, you can write like this. It is useful when you want to write many explanation lines. Also, when you have code you do not want to use but want to keep, you can comment it out so it will not run. Okay. This gets a bit technical, but it's quite important, so let me explain. There is a concept called types. Inside computers, everything is shown is just 0 and 1. For example, if you have the number 65, it is shown in binary as 0, 1, 0, 0, 0, 0, 0, 1. On the other hand, character A is also shown as 0, 1, 0, 0, 0, 0, 1. So from the computer's view, it cannot tell if it is a number or character just by looking. In program languages, we need to tell the difference between this is an integer or this is a string. This is called a type. In Python, we commonly have an integer type, floating type, floating point type, string type, and Boolean type. In Python, you don't need to specify the type. In other languages like C or Java, you have to say it is an int or something, but in Python, this is not needed. If you cannot remember what type of something is, you can use the type function, this one, to look inside. When you use type with X, it shows class int, which means this is int type. The reason I'm telling you this is because you cannot calculation with different types sometimes. If you have numbers, it is fine. X is 10 and pi is 3.514. So there are integer and floating point types. But their addition is 13.14. However, if we put x is 10, we put 10 in x and hello as a string in MSG, and try to add them, you will get error. Error. It says addition between integer type and string type is not supported. An error happens when computer cannot understand an operation or when you do something invalid. In the previous example, the cause is trying to add things that cannot be added. The error message tells you what kind of error it is and which line it happened on. For example, this one kindly tells you that line 4 has a problem. So by reading the error message, you can find where the mistakes is and why the error happened. So unsupported parent types. So if you want to treat a string and a number at the same time, you need to explicitly convert the type. When you want to add them as a string, you can do this to convert it to an integer. Sorry. So when you can use str, so this is string, to change the integer 10 to a string, and then you can add them. So 10, hello. Then also, if you have one, two, three as a character, it is a string because it is surrounded by double quotes. But if you want to add it to the integer, you can do this to convert it to integer type, and so int. And 1, 2, 3 plus 5 equals 128. Actually, even in addition between integers and floating point numbers, Python automatically does type conversion for you. This is called implicit type conversion. So when working with data of different types, there are cases where Python can automatically handle it and cases where you need to manually match the types. Okay. In Python, we often use a data structure called a list to handle multiple values together. We use square brackets to write them. Here is an example. You can also have nothing inside. If you want to know the length, so you can use len, so length. Uh, for my for my list from before has 5 elements, so it shows five. So empty and the list is empty, so it shows 0. When you want to access element in list, uh, you can do something like this. The order corresponds to 0, 1, 2, 3, 4. You can get first element with numbers 0, bracket 0. So the next element is 20. If you use number 2, int number 2, then 10, 20. Oh, sorry. Sorry, yes. 10, 20, 30. So this corresponds to 30. An important element of programming is control structures. Uh, the if statement is the structure that allows you to branch processing based on condition. You write it like this. Here is how it works. First, how so oh, first we put 75 in the score. When the score is 80 or more, this will be shown. When the score is 60 or more, then this will be shown. The else part activates when none of the case above apply. In this case, the score is 75. So since 75 is not 80 or more, so this does not run. Then we check the next line, 65, which is 60 or more. So you need extra classes is printed. If we change this to 100, you passed would be printed because 100 is 80 or more. If we change it to 50, uh, it doesn't match any condition. It's not 80 or more, and it's not 60 more. So it goes to other case. So your file would be printed. Hey. There are other comparison operator like greater than or less than. When checking if something is equal, we use equal signs twice. We would like to use just equal, but the assignment symbol already uses equals. So we have to write it this way. For not equal, we write here. The elif and else parts can be left out. The program will still work somehow. For example, like this. When the score equals 75, it shown this. What happens where this is different number? If we change it to 76, nothing is printed. This is because we say to output something when it's 75, but we didn't say what to do when it's not 75, so nothing happens. Let me introduce one more thing. There is something called a for loop. It's used when you want to process items in a list one by once. This is one of the most useful features that makes programming worth doing. For example, let's make a list of fruits. When you write for like this, normally program runs from top to bottom. But in this case, it performs this process for each element inside. Now let's look at how this works using helpful tool calling Python Tutor. Again, okay. When the first line runs, we have a list called fruits with apple, banana, orange, and orange in it. Apple is at position 0, banana at position 1, and orange at position 2. When this runs, the fruit variable first taken apple here, it outputs apple. So apple is printed. Normally, the program would go down to the next line, but in a for loop, it accesses all elements in this list. So it goes back to the first part, and since we are done with apple, it moves to banana, like this. Now banana is in fruit. When we put output it, banana is printed. Then we go back again, and the next element is orange. We put orange in fruit, and when we put output it, so orange appears. When we finish, we've seen all the elements, so we end this process and move on. So the output is apple, banana, orange. Another thing often used with for is range. For example, like this. When you want to do this 5 times, if you write range 5 like this, it's like having 0, 1, 2, 3, 4 in I. This range 5 gives us each element one by one. So if you change this 5 to 3, it becomes 0, 1, 3, 2. It goes up to 1 less than the number you give. If you change this to 10, it will go up to 9. Okay, so besides for there is also something called while loop for repetition. A while loop keeps repeating the content inside as long as this condition is true. Let's try it out. Hmm. First count is 0. Since 0 is less than 3, we go inside. Then this print output ones. You might be wondering about this part. The left side count, we are assign count plus 1 to it. So count plus 1, count is 0. So 0 plus 1 is first calculated, and count become 1, like that. Here, please look at here, 0 to 1. Then we go back here. Now for the while part is 1 less than 3. Yes. So we go inside and 1 is printed. Next 1 plus 1 is 2. So count become 2. 2 is still less than 3. So we go inside again. And the same things happen and it becomes 3. Now 3 is not less than 3. So the process ends. So after the while loop finished, if we print count, the last value of count is 3. 3 is, so if you write print count, so 3 is printed. Okay. Okay, let's skip this part. Oh, this is Python has many operator, but let me introduce some commonly used one. Plus equal, this one, perform addition and assignment at the same time. So same, it is same as x is equals x plus 3. Okay, so similarly, x minus equal 2 means the same as x equal x minus 2. Okay, now, okay, okay, let's take a break. Okay, now let us start talking about simple linear regression. The main object for today the following 3 points. To understand what simple linear regression is, to understand how many parameters in simple linear regression are determined using a least square method. Furthermore, to learn the specific algorithm and aim to apply this method to given data in practice. First, I will talk about the simple linear regression is and its purpose. The motivation for a simple linear regression is to express the data trends with a simple formula. In particular, the basic idea is approximate with a straight line. When we can express data with a straight line, it becomes possible to make predictions for unknown data. For example, think, sure. So think about spring element. Let us say you have data on the relationship between the weight handling from a spring and how much spring stretches. If you can approximate this relationship with a straight line, you can predict how much the spring will stretch for weights you have not yet tested. Also, by looking at the coefficient, you can understand the characteristic of the spring. There are other examples like predicting length. For instance, you might want to predict length based on information such as the size of house, the distance from the station, and the age of the building. Or you might want to predict sales based on temperature and day of week. In the other hand, words, the strength of this method is that is to capture the nature of the system and enable prediction. Now let us oh, Now, let us look more specifically at what we want to do with simple linear regression. What we want to do, as I mentioned earlier, is to approximate data with a straight line. For example, let us say we have data points x1, y1, x2, y2, xn, yn. In this case, our goal is to find beta 0, so beta 0, so y-intercept, and beta 1 slope, such that, like that, here the wave symbol means approximately equal to. In other words, it means roughly equal to. If we only have two data points, for example, x1, y1, and x2, y2, and and if x1 is equal to is not equal to x2, then we can solve the following system of equation to uniquely determine beta 0 and beta 1. But when we have three or more data points, we usually, sorry, we usually cannot draw a straight line that exactly passes through all points like this. For instance, if the 3 points are not perfectly aligned, there is no single straight line that passes through all of them. So we give up finding a line that passes through all points and instead think about finding a line that is as close as possible at all points. This is where the concept of deviation comes in. This deviation refers to the difference between the actual value and the predicted value. So yi minus beta 0 plus beta 1 xi. The smaller this deviation is, the better our approximation is considered to be. Now, how do we make this deviation small? That is an idea behind the least square method. In the least square method, we consider sum of square or all deviations, that is. The idea of this square method is to choose beta 0 and beta 1 that minimize this error. Why do we square the deviation? It is because there are both positive and negative deviation. If we simply add them up, the positive and negative value would cancel each other out, making the deviation appear smaller than it actually is. Of course, taking the absolute value is also an option, but absolute value can be mathematically difficult to handle. That is why we use square here. Squaring makes the function smooth, which makes it easier to find the minimum value by differentiation. So the next step in the least square method is to find the parameter that minimizes this error. So if we jump ahead a bit, the conclusion is that the value of beta that minimizes the error can be found at the point where the derivative of L equals 0. In other words, the punchline uh, is that the value of beta that given the minimum value is found by solving L prime beta is equal to 0. Moreover, this result can be calculated explicitly using mean, variance, and covariance. But if I just state the conclusion right away, it would not meet the object of this class. So from here, I will explain why we look for the point where the derivative is 0 using specific data. Okay. Since the original problem is complex, let us first proceed with the simplest assumption to approximate with a straight line passing through the origin. In other words, we will consider function of the form. Here, we assume the y-intercept beta 0 is 0. In this case, the predicted value for xi is beta xi. Uh, so deviation is yi minus beta I xi. The problem is to find the value of beta, the minimized L beta, which is the sum of square of all these deviations. Now, let us look at some specific data. In this case, the deviation for each point, the first point is so the what? Uh, so observed value is 2.5. So expected value is 50 times better. So second point is observed value is 5.1 here. So expected value is from the x value my 100 times better, like that. The sum of square of all these deviation is L beta. When we expand L beta, we get the following quadratic function. This is a typical quadratic function. So how do we find the minimum value of quadratic function? That is right. We can find the minimum by differentiating and looking for the point where it is equal to 0 by completing this square. Uh, if we complete the square from this, we can see the L beta is minimized where beta is 3,490 over 70. Okay, this value. So around approximately 0.05. This line is, so this line, so y equal 0.05x line is the one that best fits the data. When we actually draw the graph, we can confirm that it fits on the data point quite well. We can also differentiation if we differentiate the area L beta with respect to beta, we obtain L prime beta here. We get the same minimum value position as before. In other words, in the least square method, important point is to find where the derivative of the sum of square deviation with respect to beta equals 0. Now let's return to the original problem. So far, we have considered the special case where the y-intercept beta 0 equals equal to 0, but generally simple linear regression predict using a straight line of this formula. In this case, the sum of square deviation is here. If we calculate so let's calculate using the previous data. We obtain here. This is a function with two variables, beta 0 and beta 1. When we draw the graph, it looks like this. The counter lines look like this, and we can see where the minimum value might be. Now we need to find out exactly where this function takes its minimum value. Yeah, when we had one variable, how did we find the main value? That is right. We use the method of differentiating the function and finding the point where the derivative equals 0. For example, where is a function like L beta, and yes. So what do we do when there are two variables? That is when we have to parameter beta 0 and beta 1. In this case, we need to find the point where the derivative with respect to both variables equals 0. This is where partial derivative become important. The idea of partial derivative is to differentiate with respect to each variable independently when there are multiple variables. And we need to answer the question, do the point where the partial derivative equals 0 gives us the minimum value? There is something I want to confirm here. To the points where the partial derivative equals 0 really give us the mean value. As a concept, you can intuitively understand that the bottom valley, the deepest part of parabola, the slope becomes 0. However, this alone is not a mathematical explanation, just saying it seems like would be that way. It's not enough. So with the following proposition, the proposition states that if the function g is convex, then it takes its minimum value at the point where all partial derivative equals 0. Convex functions here refer to what we have seen in high school as a downward convex function, like a parabola. For functions that satisfy this property, it is granted that truly takes their minimum value at the point where all partial derivative equals 0. Now let us properly prove the proposition we mentioned earlier. Let us assume G is convex. Okay, we define one-dimensional path from from point X to point Y as H1, H lambda. Using this H lambda, so from this definition, by dividing it by lambda, we obtain this inequality, this part. So here becomes H lambda. So we obtain here. As lambda approaches 0, the right side approaches the derivative of the composite function gh. Uh, Using the formula for differentiating composite function, we obtain here. Here, H is here. H is defined as here. We obtain dhi d lambda is equal to yi minus xy. So we obtain from here and here, we obtain this inequality. So this proves the proportion. With this proportion, we know that L is minimized at the point hat beta 0 hat and beta 1 hat, where all partial derivatives equal 0. Let us actually compute the partial derivative of L. So in the following, we'll work hard to calculate each of them. We obtain like this. By using the mean value of x and y, we obtain here. Next, we calculate the partial derivative with respect to beta 1. We obtain like that. So by using the variance and covariance, we it can be, so we obtain this formulation finally. So anyway, this expression is a bit complex, but we can be organized using variance and covariance. So using these partial derivatives can be rewritten as like this. Now that we have come this far, all we need to do is solve the system of equation where both partial differentials equal 0. Solving this system of equation, we get beta 1 hat and beta 0 hat. So these are y-intercept and slope of the regression line obtained by the least square method. Here. So after going through all this theory, let us verify these formula by actually calculating them. Here are 3-point data based on this. Please first calculate the means, the variance, and covariance, and finally use the formulas, this one, to find beta 1 and beta 0. Okay, let's take a break. So please try this problem. Okay, let's restart. The data point we were given earlier here. For x, we have the mean of -2, 0, and 2, which is here. So next, for the mean of y, the mean of minus 0 0.1, 1.2, and 1.9 is 1. Now let us calculate the variance and covariance. First, the variance of x. Variance is the average of the squared differences from the mean. Since the bar x is 0, in this case, we just need to the average 4, 0, 4. So the variance is 8 over 3. Now we have calculated so next, the covariance is finally 4 over 3. So now that we have calculated the variance and covariance, let us find the slope beta 1. This is the covariance divided by the variance, so 1 over 2. The y-intercept beta 0 is found using the following formula. We obtain 1. With only 3 points, we could do calculation by hand, but if we have 100 or 1 million data points, it would be impossible to do by hand. This is where Python implementation comes in. A useful library for numerical calculation in Python is NumPy. This library makes vector and matrix operations easy, so we can write the least square method calculation consistently using dot product. Now, let us treat x and y, vector 1, vector x, and vector y that appear earlier as vectors. In this case, the slope beta 1 of the regression line can be written using the centered vector. So this is this is minus each component. So in other words, we divide the dot product of the centered x and y by dot product of the centered x with itself. And beta 0 is found using here. With the calculation method, we can quickly find the regression line 100, 1, or even 1 million data points. Now let us how to actually write this using NumPy. First, we prepare the data point at least. When we want to calculate the mean, we can easily find it using np.mean. Next, the formula to calculate the slope beta 1. This is a dot product of centered x and y divided by the dot product of the centered x with itself. The y-intercept is here. In this way, we can quickly calculate beta 0 and beta 1. To summarize, we can quickly calculate beta 0 and beta 1. Okay, so we can confirm from the graphs that the regression line calculated in this way fits the data very well. Okay, now let us check the code. So please click here. And please check this link. So you can reach here. Now let us the code. No, I would like to move on explain you code using NumPy. The approach is the same as our previous formula explanation, where we will check step by step. First, what is NumPy? It is a Python library that allows you to perform array operations and array matrix calculation efficiently and easily. When you actually use NumPy, vector and matrix calculation becomes much easier. To use NumPy, you first need to declare I am going to use in NumPy at the beginning. Here. So you should write, we have to write import NumPy as NP. So here, connecting. So just wait a minute. Okay. So let's run this. So press or play button or well, shift and enter. This is like a magic spell that say the way we'll use NumPy with short name NP. From now on, we will use NumPy's features through this NP. Next, let's create an array. In NumPy, you can create arrays from Python lists using the function np.array. this one. When you write this, when you write this one-dimensional array is created. Now, if you want to take element out of this array, like this, you can use indexes just like with lists. This will get the first element. So like lists, you can use indexes to starting from 0 to extract the element. So in this case, the first element is 10. Also, if you use the index -1, you can get the last element. This is the same usage with the list. Next, let's check the addition and multiply array. In NumPy, addition and multiplication of arrays are done element by element. For example, so let's try here. If you run ARR1 plus ARR2, then 1 plus 10 is 11. So 2 plus 20 is 22. So 3 plus 30 is 33. And you get the result 11, 22, 33. Multiplication works the same way. If you run AR1 times AR2, and you get the output 10, 14, 19. As you can see, the calculation is done for each corresponding element. Now there is an even more useful feature called broadcasting. Broadcasting is a mechanism where NumPy cleverly extends the process operations between arrays or scalars with different shape or size. For example, multiplication of an array on the number, like that. What happened? It multiplies each element by 20. So 10 times 20 is 200. 20 times 20 equals 400. 30 times 20 equals 600. So the result is here. So 200, 400, 600. The subtraction also works. So the result is -10, 0, 10. This is a feature further about casting, which automatically applies a single value to all elements of an array. Furthermore, in NumPy, you can easily do vector and matrix operations, especially in a product. Here, for example, let's say we have these two vectors, x and y. If we want to calculate the inner product, you use np dot here, np dot. The calculation is 1 times 2 is 2. 2 times 3 is 8, 6. So 2 plus 6 is 8. So 3 times 4 is 20. So 8 plus 12 is 20. So we obtain 20. Okay. So the output is 20. Statistical processing is also easy. For example, if you want to calculate the average, you use np.mean. If you want to calculate variance or no. So standard deviation, please use np.sdd. The sum can be calculated using np.sum. Now that we have all these functions, let's look at how to call the single regression calculation we did earlier using Python. So the steps are prepare the data point as NumPy arrays, calculate the mean using np.mean, calculate the inner product using np dot, find the slope beta 1, find the y-intercept beta 0. If we calculate in this order, we are good. Here is actual code looks like. Finally, when you want to visualize this regression line in graph, we use a library used called matplotlib. So we need to press here and press here. We obtain sorry. We need we need to okay here. Obtain here. This way you can see how the line fits the data point properly. This way you can see how the line. So now let's look at generating data using random numbers with NumPy. As I explained at the beginning, entering the data likes here. So point is 2, 3.1, 3.95 by hand every time is troublesome, right? When performing machine learning experiments or exercise, it's not practical to prepare data manually every time. That's where the approach of automatically generating data using random numbers comes in. First, random numbers that can take any value, 0 and 1, any value between 0 and 1 are called random numbers that follow a uniform distribution. In NumPy, you can generate these uniform random number using the function np.random.rand. You can generate, so for example, like that. For example, if you write here, you can generate 10 random numbers that uniform distribution in the range from 0 to less than 1. So indeed, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 points. So another important distribution is normal distribution. A normal distribution with the mean of 0 and standard deviation of 1 is called standard normal deviation distribution. To generate random numbers following this normal distribution, we use np.random.randn. So this n is of the n of the normal distribution. So for example, so if you write like that, this get 10 samples from a normal distribution with a mean of 0 and standard deviation of 1. Now let's use these random numbers to create artificial data needs for simple regression. First, we will imagine data with a linear regression, a slope of 2, y-intercept of 1. So the true relationship is line y equal to x plus 1. First, we create random values for x. Let's generate 100 x values. So here, that follow a standard normal distribution. Next, we multiply the slope and add. So we multiply by the slope and add the y-intercept. This gives us a straight line. So if you indeed like that, this is straight line. But in real data, there is always on noise due to the observation or measurement of errors. It doesn't for a perfect line. To simulate this, let's add standard normal distribution noise to y, like that. So this gives us data with relationship of slope to y-intercept 1 plus noise. Next, let's apply the least square method we've been doing to artificial data xy to estimate the slope beta 1 and y-intercept beta 0. This one. And we would output the calculation result here. The actual output value should be very close to original slope 2 and y-intercept y. Very similar. And this confirms that even with some noise added, the least square method can restore a close regression line. Finally, let's visualize this data and regression lines. Use plot.scatter for the scatter plot and plot.plot for the regression line. When you run this, you should be able to see how the line fits when within the scattered points. Okay, that's all. Now let us look at the in-class report for today. Here. Please submit your answer using the Google Form links shown on the last slide. The deadline for submission is Thursday, April 17 at 1 p.m. That's all. Okay, so let's try the in-class report. And if you have any question, please ask me. Okay.